Good day, everyone. I am Giancarlo Dalisan, and I am here to present our study entitled The Application of Cassava Rhizome Biochar as a Biofilter in Reducing Chromium Concentration in Wastewater of Nickel Laterite Mining in Caraga. And this study is authored by Giancarlo Dalisan and Roland Ruiz Patacsil, the students from the Department of Mining Engineering. So before that, the outline of our presentation would be first the introduction. Next is the objective of the study, followed by the methodology, results and discussions, conclusion, and the recommendations. So most industrial processes like mining contribute to inducing harm to the environment if unregulated practices are observed. As a result, there are growing concerns about living within the environment's quality standards. Owing to community health issues and environmental laws, polluted mining wastewater cannot be reused or returned to the atmosphere without treatment. So to deal with heavy metal contamination, biosorption is a promising technique for removing contaminants from wastewaters because it is less expensive and more environmentally friendly than other methods. Biosorption processes rely on feedstocks or biomasses, which are typically agricultural waste, forest wood, and sewage industrial sludge. Cassava waste consists mainly of rhizome, and around 4 million tons of the agri residue is available annually. Thus, cassava rhizome has a high potential for use in the production of biochar to remediate heavy metal concentrations in nickel laterite mining wastewater. And here's the objectives of our study. First is to utilize the cassava rhizome biochar as a biofilter, and to evaluate the effectiveness of cassava rhizome biochar as a biofilter for treating the nickel laterite mines wastewater. So this is the methodological framework of our study. So first, the preparation of cassava rhizome biochar, and then collection of cassava rhizome. And cassava rhizome samples from Mainit, Surigao del Norte were used in this study. The samples were cleaned and naturally air dried and stored in a room temperature. And for the preparation for pyrolysis, cassava rhizomes were cut to sizes ranging from 30 to 50 millimeters. And the carbonization is carried out by slowly heating the cassava rhizome in the absence of oxygen in a metal container. So the design for filtration, collecting mine wastewater sample from the settling pond, and testing the specimen results, evaluation, and the analysis. So this is the documentation for the cassava rhizome biochar production. And in this figure, we used different numbers of cycles. One feed for columns A1, A2, and A3. Then two feeds for columns B1, B2, and B3. And then three cycles for C1, C2, and C3. And the final 100 ml of the effluent of each column was collected for analysis. We also have here the settlement for 1 hour, results and analysis, and then evaluation of the results. So the figure 3 shows the biofiltration process in treating the mine wastewater, where the filter column is made up of porous materials such as sand and gravel, as well as the biochar generated from cassava rhizome. 9 400 ml beakers were filled with 200 ml of wastewater sample, and every beaker was labeled with A1, A2, A3, B1, B2, B3, C1, C2, and C3. And beakers A1, A2, and A3 were filled into columns 1, 2, and 3 using only one cycle. And Bs were also filled into columns 4, 5, and 6 using 2 cycles, and Cs for 7, 8, and 9 using 3 cycles. And 9 1.5 liter plastic containers we used to make the columns for the biofiltration. So this is the actual representation of the biofilters created in the assay laboratory in Caraga State University, and this is just a lab scale manner. And for the results and discussions, the 250 ml from wastewater sample was analyzed to determine the initial chromium concentration using the ICP-OES, or the inductively coupled plasma optical emission spectrometry at Davao Analytical Laboratory Incorporated. And it was found out that it contains chromium as shown in the table below. So we have here the concentration is at 7.7 parts per million, or 7.7 milligrams per liter, using the standard methods for examination of water and wastewater 3120D. So these graphs show the reduction efficiency rate using the different numbers of cycles. So we have here 96.35% for A1, 96.38% for A2 and A3, and then 97.54% for B1, 97.52% for B2, and we also have 97.75% for B3. And for the 3 cycles, so the C1 has 97.75%, C2 97.77%, and C3 same with C1, 97.75%. So these are the results obtained from the water test. So the summary of the results, we have here the before and after concentration and the reduction efficiency rates of each column. So table 3, using one-way analysis over variance post hoc test for significance of cycles. As what you can see, we have learned that the null hypothesis must be rejected given the fact that the value of P is less than 0.05, and that means the alternative hypothesis should be accepted or considered. So to conclude the study, Cassava Rhizome Biochar as a biofilter was utilized using slow pyrolysis method and successfully applied to reduce target heavy metal, specifically chromium, from the wastewater of nickel laterite mining company in Caraga, and shows promising results. Reduction efficiency rates using different numbers of cycles, the 1 cycle, 2 cycles, and 3 cycles of feeding the wastewater sample through the CRBC or the Cassava Rhizome Biochar were 96.37%, 97.54%, and 97.76% respectively. And for the recommendations of the study, first is to analyze other heavy metals content in order to evaluate the effectiveness of Cassava Rhizome Biochar as biofilter in reducing the amount of heavy metals present in the wastewater. Next is to apply the CRBC to the actual settling pond. Third is to create a prototype or a design mechanism intended for Cassava Rhizome Biochar as a biofilter in reducing heavy metals. And lastly, use other tests using Cassava Rhizome Biochar or CRBC as a biofilter for treating mine wastewater. Thank you so much.